Hi, in this video what I'm going to do is look at a few different situations where we want to represent preferences in a specific kind of way and try to think about two things. What would those indifference curves look like? And what kind of mathematical utility function might give us that kind of indifference curve map. So I'm not going to go through the basic ideas of what indifference curves are or what utility is. I'm going to assume you already know that. And what we're going to do is go through several different kinds of preference types we might want to model and see how we might be able to represent those graphically and as a function. So the first kind of utility function I want to look at is just the most common one that I see everywhere, which is the Cobb Douglas. And let's just notice what some of the things are about that. So COBB-DOUGLAS. The Cobb Douglas kind of utility function you will see written two different kinds of ways. One way is for people to write it this way. This is the way I prefer. Utility equals, there might be a multiplier here, some number a. That's not necessary, and it's actually kind of irrelevant for utility purposes. But some number a times x raised to the, say, little a, times y raised to the little b. So this is a kind of a general looking Cobb Douglas utility function. Every once in a while you will have someone who will write a more simplified function for a Cobb Douglas that might look like this. Utility equals x to the a times y raised to the 1 minus a. In this sort of simplified version, what you're doing is you are requiring that a and 1 minus a add up to 1, that those two exponents add up to 1. Now that's not necessary, but it does simplify the utility function quite a bit, and actually it's good enough for utility to use a function like this. Usually in my classes I'll use something a little more general because this kind of Cobb Douglas function that's more general, the a x times x to the a y to the b function, carries over into discussions of production functions using Cobb Douglas very well. But for utility, you can get away with something like this, and it does just as well. Now, let's talk about what these indifference curves look like from a Cobb Douglas real quickly. So if we have our y-axis and our x-axis here, then an indifference curve for a Cobb Douglas is always going to have a shape kind of like this. Now, depending on what these two exponents are, a and b, you can get different shapes. But it's basically going to have this kind of downward sloping property where the indifference curve approaches, so I'm drawing an arrow here, the indifference curve approaches the y-axis and the x-axis, but it never touches. So it basically asymptotes out somewhere, or it could have a shape kind of like this. But the point I want to raise here is a Cobb Douglas never touches the x or the y-axis. Now why is that? Rather than memorizing that, let's just make sure we understand why that is. Because what if it did touch the x-axis down here? What if it did touch? Well, what that would imply is that y equals 0. And if you're consuming no y, and you're consuming however much x you are, remember what an indifference curve does is tell you all the combinations of points where the utility equals some number, say 10, right? Or we could just say utility equals some fixed amount of utility u naught, right? Where we just mean that's some number, could be 10, 20, or 5. If it hits the x-axis, then that means that y is 0, and what's going to happen to this function if you plug in 0 for y? Well, in either case, you're going to be multiplying 0 times everything else in the equation. 0 times everything else in the equation, and that's going to force the amount of utility that you get to be 0. So these things can get close to the x-axis, but can never actually touch. You can't have x equals 0 or y equals 0. Now that's okay in a lot of situations, but it might not work for everything. So whenever you use utility functions to model people's behavior, a Cobb Douglas is always going to have, it's always going to tell you that the person buys some x and some y. The amount of x and y or y will never be 0, okay? So that's one common, and that's what most of my videos are based on. But I want to make sure you know that that's not always going to be the case. So let's move on to another possibility here. So let me describe a situation for you, and let's draw some indifference curves, and then let's talk about what kind of mathematical function might generate that kind of indifference curve. So here we have y, here we have x. So in this situation, let's think about x is a good. X is something that you like. And in this case, let's think about y is something that you're indifferent to. You don't care. So y is not good and not bad. So not good, not bad. First, let's think about what indifference curves would look like in this situation. And then let's think about a mathematical scenario. So let's plot a couple of points here in our axis. So here, let's see. Let's suppose that you had 1x and 1y. Let's think about some points that would be on the same indifference curve as this point, and some points that would not be on the same indifference curve. So let me draw, so we have the red point. Let me draw a blue point. Now, this is 2 units of x and 1 y. Is the blue point going to be better than the red, or indifferent, or can you not tell in this situation? Well, the answer is that the blue is going to be better than the red because x is good. More x makes you happier. So we know that this is on a different indifference curve, the blue point, and it's on a higher indifference curve. So we get happier in that direction, happy, and in this direction, nothing happens. In the y direction, we don't get happier and we don't get less happy either. So if we want to draw an indifference curve, let's think about this point. Well, let me do a different color here. Let me get purple. Okay. What about this point where we have 2 y's and 1 x? Is that going to be indifferent to the red or better than the red? Well, I kind of gave away the answer before, but those 2 points are going to be indifferent to each other, and so will any point where I have the same amount of x and more y. So here's an indifference curve. So utility equals some number, right? U0. We don't know how much, but that would be an example of an indifference curve. And then there'd be another indifference curve here for a higher amount of utility, right? And higher here, and higher here. So increasing utility as we get more x, but no change in utility as we get more y. Now let's think about what kind of mathematical functions could give us these kind of indifference curves. What we want is a utility function that has larger utility when we increase our x, but doesn't change when we get more y. So we could have something like this. Utility equals x would work, or 3x, or 4x, or 3x squared. You know, there are all kinds of functions, and we don't know the details of which of these functions. It could just be utility equals, 5 plus x, for example, would work. Or utility equals the square root of x. We don't know. But any of these functions where y does not appear at all, doesn't impact our utility in any way, would work. Now, if you want to think about a Cobb Douglas kind of utility function, we could add y here, but add a 0 power. Because any amount of y to the 0 power is just going to be 1 and cancel out there, okay? So we could do it like that also. So this is what indifference curves look like when x is a good thing and y, you don't care about. Doesn't bother you, but it doesn't make you happy either. Okay, let's look at the next case. Okay, in the next situation, let's think about what if you wanted to try to model a situation where, let's say, x is a good thing, but y is bad. Well, let's actually do let's do the reverse here. Let's switch it up a little bit. Let's say that x is bad and y is good. Now, one thing I often think about is trying to put in a point where we would call it our bliss point. Where on this diagram would we be happiest? Let's go back and look at these other two to get an idea of what I mean. In a normal Cobb Douglas, your bliss point is going to be somewhere over here, for example. It just gives you a point to think about. As we move toward this pink point, we get happier and happier and happier. In this case, where we get more x and more y, we're getting happier. So we get happier as we move closer to that bliss point, B-L-I-S-S. In this case, the bliss point is what I was trying to get at with this happy over here. As we move to the right, the further we get over here, anywhere, it's not really a bliss point, but we could say a bliss, I don't know, region. As we get more and more x, we get happier and happier, not necessarily as we move up, but just as we move anywhere toward the right, we get happier. Now in this case, if x is a good thing and y is a bad thing, think about where we would be happiest. Where is our bliss point? Well, in this case, our bliss point on this diagram would be somewhere like up here, where we have lots of y, the good thing, and no x, right? So that's what our bliss point would look like. Now let's try to think about what our indifference curves are going to look like here. Our indifference curves, let's just pick a point to think about this. Here's, suppose we had 1. And to put this in context, a very common use of this kind of preference structure is when x is, for example, hours that we have to work, or how many hours we have to farm to get our food, and then y is the actual amount of food or other stuff, or income you can think about. And so suppose I had to work 1 day to earn $1, or 1 hour to work $1. What kind of points would make me indifferent to that? And the idea here is I would be willing to work a little bit more. I'd be willing to work another hour. And I could be indifferent working another hour as long as I got some more money in return for that hour, right? Now, we don't know how much. We're just talking about generalizations here. It might be that if I wanted to work another hour, I would need $2 more. Everyone would have different kinds of preferences here, right? And so it could be that for a particular person, these 2 points, the purple and the red, they're indifferent between. And if you want them to work another hour, you might have to give them another $2, or maybe even more, another $3, right? And so we would have indifference curves that would probably look something like this. And as we move in that direction, we're getting to higher and higher indifference curves. This isn't the normal situation, but when you're in a labor economics class, talking about work decisions and income decisions, this becomes very important. Now, what kind of function could possibly represent these kind of preferences? Now, again, there are lots of them, but here's just a very simple kind of example. Utility equals, we could say something like, as simple as utility equals y is a good thing, so maybe, I don't know, 3y minus 2x. could represent this kind of preferences, not exactly with this shape and not exactly with these preferences we were talking about, but you want somehow in your function to make it to where more x makes you less happy, more y makes you more happy. And this is just probably the simplest kind of example that you could make of something like this, where any number multiplying y, any number multiplying x. Now, of course, there are other ways to do this, but this is just a simple idea to think about. How do you connect the mathematics to the graph, to the situation? Okay, let's look at another one. All right, let's look at a kind of functional form that we call quasi-linear. Here I'm going to start with the kind of function it looks like, and then we're going to graph kind of what it looks like. A quasi-linear kind of utility function has a linear term, let's say it's y, plus the square root of x would be one example of a quasi-linear. Now the prefix quasi means somewhat, or sort of, or partially linear. And so when we graph this, let's think about what this is going to look like. So the first thing we should think about is, can this function, if we were to draw an indifference curve, can it touch the x or the y-axis? Well, let's think about a couple of points on a quasi-linear indifference curve that we might look at here. Let's just draw a couple of numbers here. 1, 2, 3, 4, 5x and 1, 2, 3, 4, 5y. So let's think about the situation. What if we had, I'll do a green point here. What if we had 4 x's and we had 1 y? Here is that point on an indifference curve. Now, can you think about any other points that would give us the same amount of utility? Well, let's see. How much utility would that be? 1 plus the square root of 4 would be 3. Can you see any other points that would also give us 3 utils? What about 3y's? If I had 3y's, I could have 0 x's, and that would also give me 3 utils. So here we go. There's another point on the same indifference curve, and these kind of have this shape where they bend a little bit as they get up to the y-axis there. Can you think of another point? What if I didn't have any y's? Is it possible to have 3 utils still? How many x's would I need? Well, 9, because the square root of 9 will give us 3. And so there's another point way over here, 6, 7, 8, 9. Where we also get 3 utils. So here's the indifference curve for u equals 3. And look, with a quasi-linear, it touches both of these axes here, both the y-axis and the x-axis. And the reason it can do that is because of this plus sign right here. Right? These two things act independently, and so if one of them is 0, it doesn't cause the whole function to degenerate to become 0 like that. Now what happens with quasi-linear indifference curves is there's going to be another one here that kind of is parallel to it. Now, what do I mean that it's parallel? What I mean is the slope of the red indifference curve is going to be the same for any x value here. All the y value does here is shift the indifference curve up by 1 unit, right? You get 1 more y, it just adds 1 more util. No matter how much x you have, it just shifts it up exactly by 1 unit straight up. And so the slope at this point, let me get a blue here, the slope of the green indifference curve there is the same as the slope of the red indifference curve right there. So the one reason we call this a quasi linear is when you get more y, that's a linear term. You always get, your utility always increases at a constant rate as you get more y. In this case, always goes up by 1. Now we could just as easily have a function like this, utility equals 2y plus the square root of x, and that would be also a quasi-linear utility function, although it would be, give us a little bit slightly different answers. What's going on here is as we get more x, our marginal utility is decreasing for each additional unit of x. But as we get more y, our marginal utility is always constant. One more y always gives us one more util. But one more x, well, we get decreasing additional utility there. When would this ever make sense? Well, a common use of a utility function like this is when you think about y as being something like money. Utility in money is going to be sort of linear. Now this isn't totally true. We don't really believe this, but it's an approximation, an easy approximation to say that as I get more money, the marginal utility is going to be more constant than the other good. So if y is money, x might be a specific product, perhaps alcohol or hamburgers or something like that. So when you compare the marginal utility for the 4th, 5th, 6th hamburger, that marginal utility is going to be decreasing quite rapidly compared to how fast your marginal utility for additional cash will go down. Because cash is good for so many things, your marginal utility goes down more slowly for cash than it will for one specific product here, like hamburgers. So that's a common use for that kind of utility function. Okay, let's look at a couple more quick examples here. Another common example that you see in textbooks, and is also very important to think about here, is complements and substitute goods. So let's think about two extreme cases here, perfect complements and perfect substitutes. And let's think about first what the graph would look like. Let's think about, I'm not going to tell you which this is, substitutes or complements. It'll be obvious though. Suppose I wanted to look at the indifference curves between dollars here and quarters. And for people who are not from the US, a dollar is 100 pennies, and a quarter is a quarter of a dollar, 25 pennies. So it takes 4 quarters to have the same amount as $1. So what would indifference curves look like between quarters and dollars? Let's look at this point right here as an example. Suppose I had this blue point right here. Suppose I had 4 quarters and $1. What other points would make me indifferent between that? Think about 2 of them. Okay, I'll give you the answers now. 2 other points would be 1, 2, 3, 4, 8 quarters and no dollars, right? And another point would be $2 and 0 quarters. Now let's think about what these indifference curves are going to look like. Well, they're going to be perfect straight lines right here. It's perfect straight line. And this is an example. Think, are quarters and dollars complements that go together or substitutes that can be substituted for each other? Well, of course, this is an example of perfect substitutes, or almost perfect substitutes. I don't want to hear any comments about, well, they're not exactly perfect substitutes. I understand, but they're pretty darn close. Pretty close. And so perfect substitutes have these straight line indifference curves. And of course, our bliss point would be up here. right? We're going to be happiest as we get up to the upper right because we'll have a lot of dollars and a lot of quarters. And again, you can make the argument, I don't want a lot of quarters because these coins can get quite heavy. I understand. They're not exactly perfect substitutes, but they're going to be pretty close. And so anytime we look at an indifference curve that is it's going to be a straight line. Let me just draw another one up here. It's going to have the same slope, right? Because the substitutability that keeps you happy is every time you go down 4, you're going to go up 1 to keep you just as happy, right? The slope here has to be -1/4 in order to keep you just as happy here. And the same thing with any indifference curve for quarters and dollars. Now, you might have as I said, you might have a slight bias towards dollar bills because these are paper and they're less heavy. You could also think about there's a sweet spot. You always want a few quarters in your pocket in case you need to put them in some kind of parking meter or something like that doesn't accept dollars. But in general, you're going to be roughly indifferent between those two things, 4 quarters to the dollar. Now let's look at the last example here that I want to look at. Let me get a new page going here. What about the other case, perfect complements? Oh, I'm sorry. Let me go back to that previous page here real quickly so that I can we need to talk about what a utility function for perfect substitutes would look like, and then we'll look at perfect complements real quickly. Utility equals, and this is important for perfect substitutes because almost everyone gets this kind of thing wrong the first time they do it, including me. I'm not trying to say that I'm perfect, but think about the perfect substitutes. Think about what kind of indifference curve or what kind of utility function could generate indifference curves for dollars versus quarters. Now, what most people do, including me the first time I did this, think is that this utility function would give it to you, that utility equals 4 times the number of dollars, I'll say D, plus 1 times the number of quarters. Now that's wrong. That's wrong. It seems right when you first write it down. Why is it wrong? Well, let's look at these 3 blue points again. And any function that tells us that those 3 are indifferent has to have the same level of utility. And let me just erase that red line. Remember, this is wrong. Let me draw a pink line through the top there so we can still see it. Let's look at this point right here, $2 and 0 quarters would give us a utility of 4 times 2 equals 8. Let's look at this point. Well, we have 4 quarters, so utility equals, well, actually that is right, I think. Well, let's look. 4 times, let's see, 4 times $1 plus 1 times 4 quarters equals, well, that gives us 8 also. So this is right. I'm sorry. See how hard this is? I wrote down the correct equation when I meant to write down the wrong equation. And this point over here, utility equals 4 times $0 plus 8 times, 1 times 8 gives you 8. So this is the right equation. I'm glad I didn't permanently do that wrong. This is the correct equation. What normally people write down is the first time is something like this, that utility, so here's the wrong version, utility equals dollars plus 4 times quarters. And what's going through people's heads when they write this down is that, well, you need 4 quarters to equal $1. But this is the right way. I double reversed myself in my brain as I was talking through it here. The right way to think about it is that the $1 gives you 4 times as much utility as each quarter. So if a quarter gives you 1 happiness, dollars have to give you 4 times as much. So this is the wrong way that I see myself and other people thinking about how you could write that utility function down. Now again, there are other ways, but as long as any function, as long as a dollar gives you 4 times as much as a quarter in terms of happiness, would work. Another example would be 8 times the number of dollars plus 2 times the amount of quarters. That represents the same preferences. This number you get for utility doesn't really mean anything. It's the relationship between the marginal utility for the 2 items that's important when it comes to preferences. Okay, sorry. Let's go look at perfect substitutes real quickly and wrap up this video. Let me insert another page here. Okay, so perfect complements, things that go together. But a perfect complement is going to be something where the 2 things have to go together. Perfect complements. And the simplest example would be, for most people, left shoes and right shoes, or left gloves and right gloves. As long as you have 2 feet or 2 hands, then in order for you to be happier, you need another of each. So for example, if we look at this starting point, what if I had 1 left glove and 1 right glove? What kinds of things would I be indifferent with? Well, what about 2 right gloves and 1 left glove? How many pairs of gloves do you have? You still have 1 pair of gloves. And that extra glove isn't going to do, that extra right glove isn't going to do much good for you. Similarly, if we look at, what if you had 2 left gloves and 1 right glove? Similarly, that's not going to do much extra for you. And so an indifference curve here is going to be lines that have right angles to them. So we could say this is utility equals 1 or 100 or whatever we call it. Some utility level. Let me erase that and put that a little bit closer here so you can actually see it. Let's just say, for the sake of argument, that that utility equals 1. What's it going to take for you to get a higher level of utility? Well, you're going to need 2 of each, right? But if you had 2 left gloves and 3 or 4 or 5 or 6 or 100 right gloves, it's not going to make you a whole lot happier. So it'll be another utility curve here. So this is an idea of perfect complements. It doesn't have to be in the proportion where you need 1 of each, like gloves. It could be that you are making cakes, and for every 1 pound of flour, you need 3 eggs, right? And you could have perfect complements in that same kind of way. Or for each cup of coffee, you need 3 teaspoons full of sugar. You could draw perfect complements a similar way. And normally, mathematically, the way we will write a utility function for perfect complements is something like this. Utility equals the minimum of x and y. In this case, how happy are you when you have 2 left gloves and 1 right glove? Well, the minimum of 2 and 1 is 1. And that tells us that you have 1 complete pair. And so that's a way to get this kind of shaped function, is the minimum function of the 2. And again, if it wasn't in the same proportion 1 to 1, you could say, well, what's the minimum of 3x and 2y, to make it a little more general. So if you, as always, If you have any questions or comments, please leave me a comment or question in the comment section below. And I hope this has helped you see several different kinds of utility functions and how they can model different types of situations that you might see.